On December 28, 1879, a passenger train entered a bridge that was believed to be one of the greatest engineering achievements of its time. Strong winds were sweeping across the River Tay that night. Minutes later, the center of the bridge collapsed. What happened in those final moments would forever change how large structures are designed. In the 19th century, travel across eastern Scotland was slow and complicated. The distance between Edinburgh and Dundee was only about 74 kilometers, but the journey could take more than 3 hours. Passengers had to switch trains multiple times and cross rivers using ferries. A direct railway bridge across the River Tay promised to transform transportation in the region. The idea became reality under the leadership of engineer Thomas Bouch. The project aimed to create a long lattice girder railway bridge stretching more than 3 kilometers across the river. It would be one of the longest bridges in the world at the time. The structure included dozens of spans supported by iron columns anchored into what was expected to be solid rock beneath the riverbed. It was an ambitious project and a proud symbol of industrial progress, but construction did not go as planned. Engineers soon discovered that the rock foundation lay much deeper than expected. This forced changes to the design. Some structural elements were modified, materials were adjusted, and budget pressure began influencing decisions. The bridge still moved forward, but not exactly as originally intended. In June 1878, the Tay Bridge officially opened. At the time, it was celebrated as an engineering triumph. Newspapers praised the achievement, railway travel became faster and more direct. For a moment, the bridge represented the future. But beneath its success, questions about structural strength and wind resistance remained unresolved. December 28, 1879 began quietly. The morning sky was clear, but by afternoon weather conditions began to change. Rain moved in, winds intensified, and barometric pressure dropped rapidly. By evening the storm had grown severe. Strong gusts swept across the River Tay, shaking buildings and rattling windows throughout Dundee. At around 7 p.m., railway staff monitored operations near the bridge. Signals confirmed that a passenger train was approaching from Burntisland toward Dundee. Despite the storm, the line remained open. Shortly after the train entered the bridge, inside passengers likely felt the wind pushing against the carriages as the locomotive moved across the exposed structure. Observers near the river later described strange details. Lights from the rear of the train appeared to sway from side to side in the darkness. Sparks were seen near the wheels, possibly caused by friction or debris on the track. Then suddenly, visibility dropped. Wind, rain, and darkness surrounded the bridge, and within moments something went terribly wrong. A large central section of the bridge failed. Multiple spans gave way under extreme wind pressure. The train, along with part of the structure, fell into the river below. The storm continued, making rescue efforts nearly impossible that night. All passengers and crew on board were lost. The next morning revealed the scale of the disaster. Large portions of the bridge were gone. Iron supports stood broken above the water. Debris from the railway and carriages was scattered in the river. The event shocked the entire country. Newspapers across Britain covered the story, trying to understand how such a modern structure could fail so suddenly. A formal investigation was launched. Engineers, inspectors, and government officials began examining the remains of the bridge. Their goal was not only to determine what happened, but to understand how to prevent similar failures in the future. The findings would reshape engineering practices. The investigation identified several critical issues: Design weaknesses reduced the bridge's ability to withstand powerful lateral winds. Some materials used during construction were not as strong as required. Maintenance and inspection practices were not consistent enough for a structure of this scale. And most importantly, wind forces had not been fully understood or properly calculated during the design phase. At the time, engineers were still learning how large structures reacted to dynamic wind loads. The Tay Bridge faced strong horizontal pressure from powerful gusts sweeping across open water. Without sufficient reinforcement, sections of the bridge began to shift. Connections weakened, supports lost stability. And once the first structural elements failed, the collapse spread rapidly through adjacent spans. The investigation concluded that the disaster was not caused by a single failure, but by a combination of interconnected decisions and limitations. Design assumptions reduced the bridge's ability to withstand extreme conditions. Material selection weakened critical structural elements, and construction constraints limited proper reinforcement. Together, these factors created a system that could not endure the storm. As the lead engineer, Thomas Bouch became the central figure in the investigation. Once widely praised, his professional reputation was permanently shaped by the conclusions that followed. But the story did not end with blame. The collapse forced engineers worldwide to rethink how bridges were designed. Wind resistance became a major factor in structural planning. Testing standards improved. Inspection systems became stricter, and safety margins increased. The Tay Bridge disaster became a turning point in the history of civil engineering. Despite the tragedy, the need for a crossing over the River Tay remained. Construction of a new bridge began in the early 1880s. This time, engineers applied lessons from the past. Stronger materials were used. Design calculations were more advanced. Wind loading was taken seriously. The new bridge opened in 1887, and it still stands today. Even today, parts of the original bridge can still be seen above the surface of the river, quietly marking the place where the structure once stood. Over time, this site has become a reminder of both human ambition and the challenges engineers faced in an era of rapid industrial progress. Memorials across the region honor the passengers and railway workers connected to the event, while historians and engineers continue to study the story as an important chapter in the development of modern structural safety. The Tay Bridge disaster is not just a story about failure, it is a story about learning, about how mistakes lead to progress, and how engineering evolves through experience. Modern safety standards, structural simulations, and wind-resistant design principles all trace part of their history back to events like this. Today, large bridges are tested against conditions that 19th century engineers could only estimate. Computer modeling predicts wind behavior, materials undergo rigorous certification, and monitoring systems track structural stress in real time. But the question remains, would modern engineering have prevented the collapse entirely? Or did this disaster have to happen for those lessons to be learned? The fall of the Tay Bridge changed how the world builds, not through fear, but through understanding. If you're interested in real engineering stories, historical disasters, and the lessons they leave behind, subscribe for more documentaries like this.